Hello. In this video, we will discuss sedimentary rocks. We will first review what a sedimentary rock is, and we will break them into three groups. We will look at each group, talk about how the rocks in the group are formed, and then look at their depositional environments. We will finish with an edible geology activity. So let's begin. Before we move on, let's review some vocabulary. Lithify. Lithify means to change to stone or to petrify, or to consolidate from a loose sediment to a solid rock. Clast. A clast is an individual grain or fragment of sedimentary rock formed by the breakdown of other rocks. Cement. Cement is mineral material that occurs in the spaces along grains or clasts of consolidated sedimentary rocks, binding them together. An aeolian, pertaining to the wind. Sedimentary rocks are rocks that have formed at the surface of the earth from pre-existing rocks or from pieces of organisms that once lived. They often exhibit distinct layering or bedding. The material can be carried by water or wind, dissolved in the water, or accumulated in place as organisms break down or die and decay. Today, we will discuss the sedimentary rocks in three groups. We will first review the clastic sedimentary rocks. We will then review biochemical and organic sedimentary rocks. And we will finish with our chemical sedimentary rocks. To kick off this discussion, we will review sorting and transport. The type of clastic sedimentary rock you get depends on the amount of energy, or how fast the water is moving or the wind is blowing, and how far the material has traveled. Simply put, in fast-moving water, like a swift-moving river, very small to very large pieces of material can be plucked up and transported. In bodies of water that are moving slowly, only smaller pieces of material can be picked up. As energy decreases, bigger rocks fall out or are deposited, making conglomerates, followed by sandstones when the energy decreases again. When the energy is gone, the smallest sediments can fall out. These would be the sediments that would make things like mudstones. In the photo on the left, we can see a rock with large clasts in the bottom and with no clasts on the top. This indicates the energy decrease between deposition of the rock on the bottom and the rock on the top. So if we look at the diagram in the top right, we can see that with increasing energy, we get bigger pieces of material. And as the energy decreases, the material gets smaller and smaller, to the point where visible grains cannot be seen. Now, moving our attention to the diagram in the bottom right, we can see a neat depiction of sediment types and the rocks they will become once lithified. We start in the low energy environment with a clayey mud, which, if lithified, will turn to shale. Moving up a step in energy, we have sediment that is made out of silty mud, which, when lithified, will turn to siltstone. Then, the next higher energy environment, we have sediment made out of sand, which will become a sandstone. And finally, in the highest energy environment, we have gravel, which, when lithified, will become a conglomerate. We will take a look at each of these rock types again in a moment. This diagram nicely shows some characteristics on transport, sorting, and rounding of the materials. We can see that the coarser sediment is usually found closer to its erosional source, and fine-grained sediment is found farther away from its source. Material becomes more and more sorted the farther away from the source it is transported. Particles also become more rounded the farther away from the source they travel. Let's take a look at some examples of clastic sedimentary rocks. Clastic sedimentary rocks are made up of clasts from other rocks that have been broken down by the process of weathering or erosion, transported and deposited somewhere else, and cemented together by burial and compaction and turned to stone or lithified. These pictures show the four main types of classic sedimentary rocks. We have sedimentary breccias, conglomerates, sandstones, and mudstones. Let's look at each one of these in more detail. The photo on the right shows a sedimentary breccia. Sedimentary breccias are poorly sorted and have angular clasts, indicating that they haven't traveled very far. If we look at the photo, we can see that the clasts are pretty angular and jagged, and sorting is not present. It's just kind of a jumbled mess. Sedimentary breccias can be formed by mass movements such as debris flows or in areas where flash floods rapidly bring a chaotic jumble of broken pieces of rock in a variety of sizes out of the mouth of a canyon. The photo on the left shows a big apron of material coming out of the mouth of a canyon. The apron is called an alluvial fan. The alluvial fan is made up of layers and layers of jumbled rocks. These jumbled rocks are buried by future generations of flash flood debris, burying, compacting, and cementing older rocks, or turning them to stone, also known as lithification. The stone that is produced in this environment is called a sedimentary breccia. Conglomerates. Conglomerates have rounded clasts, as we can see in the photo on the right, and have more sorting and rounding of the clasts than sedimentary breccias because the material has traveled farther from its source. They are deposited in high energy environments that are capable of carrying large clasts, like a swift moving stream or a river. We can see the stream in the photo on the left looks like it's moving pretty fast. Most of us have seen or touched a sandstone, and most of us have put our toes into or have played with the material that makes up a sandstone. Sandstones are made up of very well sorted materials. Think of picking up a handful of sand on the beach. There's no clay and there are no boulders, just sand. This is due to sorting. Boulders would have been deposited before the sand fell out of the water, and as the water traveled on, the smaller, lighter clay particles went with it, leaving behind just the sand. Reworking by wave action further sorts or cleans out the finer particles, making beautiful, soft sand. There is another common transportation agent of sand. This would be the wind. Most of the time, the wind isn't capable of picking up pebbles and boulders, thank goodness, but it is capable of picking up sand-sized particles or smaller particles, also known as dust. Sand is commonly plucked up by the wind and pushed or carried to another area, making large sand dunes. Here in Nevada, you may have seen some of these sand dunes. A large and popular dune is Sand Mountain outside of Fallon, or there are dunes north of Winnemucca. Dunes can also be buried, compacted, cemented, also known as lithified, resulting in an aeolian or wind-blown sandstone. Last in the water, but certainly not least, would be the material that makes up our mudstones. Mudstones are made up of the very small, very light particles that stay suspended in the water the longest. The particles will settle out when all of the energy is gone or the water stops moving. These environments, where the water is calm and not moving, include deltas, lagoons, lakes, and the deep ocean. The photo on the left clearly shows sediments suspended in the water. That would be the brownish red color you see. As the sediments move into deeper, calmer waters, they will fall to the bottom and deposit a rock that will look very much like the photo on the right, a mudstone. This diagram will be shown a few times throughout this video. It will be used to try to put the rocks we see into context. First, let's look at our sedimentary breccias. We see our sedimentary breccias are placed in the high-energy alluvial fan environment. in the top left-hand corner of your screen. Conglomerates fall into the fluvial or river and stream environments along with sandstone. Streams and rivers fluctuate with the seasons, so you may get alternating beds of conglomerates and sandstones. Sometimes the energy in a stream can decrease so much that it will allow for mudstones to form. Sandstones show up in a variety of environments, from fluvial environments to delta environments, where energy is fluctuating due to seasonal factors or tides. Big sand deposits occur on beaches or as aeolian dunes. Next up are biochemical and organic sedimentary rocks. Biochemical rocks are made up of fragments of once living creatures that have been broken down and lithified. Organic sedimentary rocks are rocks made from the accumulation of the remains of fossil plant matter. Let's take a closer look. Biochemical limestone is produced by organisms that use calcite to make their shells or skeletal structures. In the photo on the left, we can see a coral reef. As the reef grows, the older parts of the reef get broken and buried, along with the shells and skeletons of the creatures that lived and then died on the reef. As the material accumulates, it starts to bury the older material, causing lithification to happen and the formations of limestones, some of which can be very fossiliferous, like the one shown in the photo on the right. Moving on to Biochemical Chert. On this slide, we have some pictures of some organisms depicted on the left. The one on the top is a photo showing some radiolarians. Radiolarians are protists that use silica to build their skeletons. The bottom left-hand photo is a photo of some diatoms. Diatoms are single-celled algae that have a cell wall made of silica. Biochemical chert is formed by the recrystallization of silica-secreting organisms like the radiolarians and the diatoms. When the radiolarians and the diatoms die, they accumulate on the sea floor. After they accumulate, they are recrystallized and turned into a biochemical chert. Diatomite is a cool rock that can be found right here in Nevada, oftentimes with fossilized fish. Diatomite forms when the diatoms die and accumulate at the bottom of a body of water, but they are never recrystallized or never turned to chert. Coal is our organic sedimentary rock. Coal is formed from the remains of fossil plant matter that accumulates and decays in the absence of oxygen. Environments that host enough vegetation and moisture for this process to take place would be similar to the swamp shown in the photo on the left. The organic matter is buried and chemical changes occur, turning the rock into different types or grades of coal. Here's our depositional environment diagram again. We can see coal, which is placed in the lagoon setting that is rich in decaying organic matter. Limestone is placed out on the shelf. Limestone can form in the shelf and slope environment, as well as in freshwater environments like inland lakes. The same is true for chert and diatomite. However, radiolarians do not live in freshwater environments, only in the oceans. So chert found inland that are biochemical would be derived from our diatoms. Chemical sedimentary rocks. Chemical sedimentary rocks form when mineral constituents in a solution become supersaturated and inorganically precipitate. Let's look at an example. If you take a glass of water and pour a bunch of salt into the cup and you stir it, the salt will dissolve. Salt is made up of sodium and chloride, and when you stir it into the water, those bonds fall apart. So you end up with a glass of water that is saturated with sodium and chloride. If we take that glass and leave it setting out, the water will evaporate over time. As it dissolves, the sodium in the chloride will start to rebond, forming salt that will precipitate on the bottom of the cup when all of the water is gone. Chemical limestone, dolomite, chert, halite, barite, and gypsum are all formed in this manner. How does this happen, you ask? Well, water that contains these elements gets trapped inland. Similar to the glass of water, when the body of water evaporates, the elements will become supersaturated and start to bond together and precipitate in layers, forming chemical sedimentary rocks. But why isn't chert shown here? Let's explore that. For our chemical sedimentary rocks, the only depositional environment shown on this diagram are the playa lakes, or the bodies of water that are trapped inland, as the other processes we discuss happen underground. Nevada has many playa lakes where chemical sedimentary rocks and minerals can be found, including barite, halite, gypsum, and borax. In summary, sedimentary rocks are rocks that are formed at the surface of the earth from pre-existing rocks or from organisms that once lived. We discussed three groups of sedimentary rocks. Clastic sedimentary rocks, which are rocks made up of clasts and smaller sediments from other rocks. Biochemical and organic sedimentary rocks, which are made up of fragments of living creatures or the accumulation of the remains of fossil plant matter. And chemical sedimentary rocks, which are rocks that form when mineral constituents in a solution become supersaturated and inorganically precipitate. They each form in specific environments. All the rock types we discussed are plotted on this diagram, which should be familiar to you in the environments they commonly form in. Now it's time for some edible geology. For this video, we made edible conglomerates. For review, conglomerates are a type of sedimentary rock made of pebbles, sand, clay, silt, and gravel that have been cemented together by pressure and chemicals that precipitate out of the water, such as calcium carbonate and silica. Here is a list of things you will need. Remember, conglomerates contain pebbles of different types of rocks in a variety of shapes and sizes. Popcorn balls can resemble real conglomerates by adding colored marshmallows and candy like M&Ms, Nerds, gummy bears, and nuts. In addition, conglomerates are formed under pressure and cemented together by precipitated chemicals. Similarly, popcorn balls are cemented together by students' hands and by the syrup mixture. You can use any popcorn recipe. You could even do this with Rice Krispie treats. Remember, the more different colors and kinds of candy you use, the more realistic it will be. It is best if you have adult volunteers do the actual cooking, but allow the students to grease their hands and form their own popcorn balls. Students should have chosen a selection of items to add to their ball before they get the mixture so they can mix them right in as their popcorn ball cools. It doesn't matter if they examine the conglomerate before or after they make it. You may want to have some of the students examining the conglomerates while others are making their balls. For exploration, have the students look at their popcorn balls or look at their materials before they assemble the popcorn balls and have them note, what do they look like? What do they feel like? What do you think that they are made out of? This step depends on where you're doing the activity at home with only one or two kiddos, or in the classroom with several individuals. If you're in the classroom, you may want to break them into groups. In either case, they will need plenty of grease to put on their hands so the conglomerates don't stick to their hands. Once they mix everything together, make sure you have pieces of wax paper available for them to set their conglomerates on. After their popcorn is made, have them examine their popcorn ball and maybe ask them, How are popcorn balls like the conglomerates? What forces were used to make the popcorn balls? Here are some ideas to further concept development. Discuss how the popcorn balls resemble conglomerates. You can discuss class shape, size, and sorting, and what each of those mean. You can also discuss how pressure from their hands allowed for the syrup to effectively act as cement and hold the rock together. You could discuss which forces made the conglomerate and how those forces would happen in the geologic environment. As far as application goes, you could have the students find and share other recipes that may be similar to a different kind of rock, or allow them to bring in samples and they can explain how they are like a rock. You may also have the students do some research to find out where some conglomerate rocks are found and how they were formed. That's all for this video. We certainly hope you enjoyed and learned something about sedimentary rocks. Please check out our other videos to gain more geologic knowledge. Have a great day.